In this lesson, we're going to talk about applications of the derivative. Our first definition is average rate of change of y with respect to x, and it's over the interval x sub 1 comma x sub 2, and we have change in y over change in x equals, and this formula probably looks familiar, it's slope of a secant line. We have f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. Again, it's also known as the difference quotient, and it can be interpreted as the slope of the secant line. You have points P, Q, and it's the slope of the secant line between those 2 points. If we continue down here, we have the limit of the average rate of change as change in x goes to 0 is the derivative f prime of x sub 1, which can be interpreted as the instantaneous rate of change of y with respect to x. Or, again, as we're also familiar, slope of the tangent line to the graph of f at the point P, and then here's your coordinates. You can also use Leibniz's notation to rewrite the limit as dy dx, which equals the limit as change in x goes to 0 of change in y over change in x. So again, instantaneous rate of change is going to be your dy dx. Average rate of change is going to be your f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. I have a note here that says derivatives are used for rates of change in many applications. So one that's going to come up a lot is going to be physics. We have our position, velocity, and acceleration. So here we have s sub t is going to be position of a particle at time t. When you take the derivative of your position function, you're going to get velocity. So velocity, again, we have it written as ds dt, the derivative of the function s with respect to time. It's the displacement with respect to time, or instantaneous velocity. And then if you take the derivative again, you're going to get acceleration. So acceleration is the derivative of velocity, or the second derivative of the position function. And again, it's written out as acceleration or instantaneous rate of change of velocity with respect to time. If you're asked to find when the object is at rest, that means you're taking the velocity and setting it equal to 0 and solve for time. If you're talking about the object moving in the positive direction, that's going to be when your velocity is greater than 0. And positive direction could be up, forward, to the right, just depending on the context of the problem. If we're talking about the object moving in the negative direction, then your velocity is going to be less than 0. And again, this could be to the left, down, backwards, it just depends on the context. And finally, if you have to find the total distance traveled over a closed interval, you're going to take the absolute value and then you're going to go f of b minus f of a. We have 2 more definitions right here, speeding up and slowing down. For speeding up, a particle is speeding up when the velocity and acceleration have the same sign. And that will happen when the particle is pushed in the same direction it's moving. Then you have slowing down. A particle will be slowing down when the velocity and acceleration have opposite signs. This example says a particle moves along a straight line. For t greater or equal to 0, the position of the particle is given by, we have s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds, s in meters. Part A says find the velocity at any time t. To find velocity, we're going to take the derivative of the position function, and we get 3t squared minus 12t plus 9. Part B says find the velocity at time t equals 2 and t equals 4. Since we're plugging in 2 into the velocity function, I'm using the notation v of 2, and the velocity at time t equals 2 is going to be negative 3, and then our units is meters per second. And the velocity at t equals 4 seconds is 9 meters per second. Part C says find all times t when the particle is at rest. To find when the particle is at rest, we're going to set the velocity equal to 0. In this equation, I'm going to divide every term by 3. Then I factored, and when you solve, you get t equals 1 and 3 seconds. Part D says when is the particle moving in the positive direction? To move in the positive direction, that means your velocity is going to be greater than 0. So first I factored out a 3, and I'm going to divide it out from both sides. And now that we've gotten to here, I'm going to set up a number line. So on our number line, we're going to test points v of 0, v of 2, and v of 4. So using this number line, we're going to make a sign chart. I just arbitrarily chose a number to the left of 1, I picked a number in between 1 and 3, and then I chose a number to the right of 3. So what we're going to do is make a sign chart. We want to identify the intervals over which velocity is positive, and then the intervals over which velocity is negative. So we already found v of 2 and v of 4 in part B. V of 2 was negative, V of 4 was positive, and we just need to plug in 0. So here's our velocity function. When we plug in 0, we get positive 9. So we can see from this chart, so looking at our chart, we can see that velocity is positive in this interval and then also in this one. And I want to point out one more thing. Up here it says t is greater or equal to 0. So this interval, it doesn't keep going, so it starts at 0 and goes up to 1, and then from here it's going to be from 3 on. So the particle is moving in the positive direction from 0 less than or equal to t less than 1, and also t greater or equal to 3 seconds. Part E says to draw a diagram to represent the motion of the particle. So I rewrote the position functions, we had it for reference, and what I did is I plugged in 0 for t. So I wanted to find the position when time was 0, and you get position is 0. When you plug in 1 second, the position is 4. When you plug in 3 seconds, the position was 0 again. The next thing I want to note is the particle is moving in the positive direction from 0 to 1. Then it's going in the negative direction from 1 to 3 seconds. And I also want to point out that the particle is moving in the positive direction, so we're going to go right-left in this case. It's moving to the right from 0 to 1 second. Then it stops from 1 to 3 seconds. The particle's moving to the left because velocity is negative, and then it stops again. And from 3 seconds on, the particle's moving to the right because the velocity is positive. So I sketched it out. The particle starts at 0 when t is 0. It starts moving to the right until t equals 1 second. It stops at a distance of 4, and then it starts moving left until 3 seconds. And at 3 seconds, it's back at 0, and then it continues to move to the right again. So we could leave our graph like this, or we could add in little arrows to indicate direction. And there you go. Part F says find the total distance traveled by the particle over the time interval from 0 to 5. The key to doing this part is we want to focus on when the particle stops. So you have your endpoints 0 and 5. So the particle was at rest at t equals 1 and 3 seconds. So now, because we're going from 0 to 5, and then you also have these breaks at 1 and 3, you want to think about the distance traveled from 0 to 1, then from 1 to 3, and finally from 3 to 5. So I set this up. It's going to go s of 1 minus s of 0, then s of 3 minus s of 1, and finally s of 5 minus s of 3. So we're going to plug in 1 and 0 and 3 and 5 all into the position function. So I think I got everything plugged in correctly. We have s of 0 is 0, s of 1 is 4, s of 3 is 0. So I got those plugged in, and then finally s of 5 is going to be 20. And then remember, we're taking the absolute value of these values, so we get 4 plus 4 plus 20. So our final answer is going to be 28. So our final answer is a total distance of 28 meters. Part G says find the acceleration of the particle at time t and at time t equals 4 seconds. So we're starting with the velocity function, and because we need acceleration, we're going to take its derivative. So the acceleration of the particle at time t is going to be 6t minus 12. To evaluate it at 4 seconds, we're going to plug in 4. So our acceleration when t equals 4 seconds is going to be positive 12 meters per second squared. Part H says when is the particle speeding up and when is it slowing down? So I rewrote the sign chart for velocity. We had positive from 0 to 1, we had negative from 1 to 3 seconds, and then we had positive from 3 on. For acceleration, we want to look at the acceleration formula. We have 6t minus 12. When we set the acceleration function equal to 0, we get t equals 2. If we take 1 and plug it into the acceleration function, we get negative. And if we take 3 and plug it into the acceleration function, we're going to get a positive value. For speeding up, that's going to be where your velocity and acceleration have the same sign. So you can see from 0 to 1, the two functions have opposite signs. But from 1 to 2, they're both negative. So that would be where the particle's speeding up. Right here from 2 to 3, you can see that the two functions have opposite signs. And right here from 3 on, velocity and acceleration are both positive. They have the same sign, so that's also where the particle is speeding up. Slowing down is when the functions have opposite signs. So you can see opposite would be from 0 to 1. Here they were the same. Also, opposite would be from 2 to 3. Their signs are opposite. So that would be where the particle is slowing down. And then one last thing, I checked at 0. So when you plug in 0 to velocity, you get positive 9. And when you plug 0 in for acceleration, you get negative 12. So they do have opposite signs, so I included 0 in this interval. So 0 less than or equal to t less than 1, and then also when t is between 2 and 3 seconds. This example says the graph of a velocity function is given where t is measured in seconds. When is the particle speeding up and when is it slowing down? Explain your reasoning. So I labeled it v so we don't forget it's the velocity function, and I put a little number line down here that we can use for reference. So first I want to look at the velocity function being positive and negative. So from 0 to 2 seconds, the velocity function is above the x-axis, so it's positive. From 2 to 4 seconds, the velocity function is below the x-axis, so it's negative. Next, I want to think about the acceleration function. Remember, acceleration is the derivative of velocity. So since this is the velocity graph, we just need to look at its slope of the tangent line to talk about acceleration. So if you look from 0 to 2, the slope of the tangent line is negative. If we keep going from 2 to 3, the slope is also negative. So that would indicate that acceleration from 0 to 3 is negative. From 3 to 4, the slope of the tangent line is positive, so that would mean the acceleration is positive. So speeding up is where velocity and acceleration have the same sign. They're either both negative or both positive. So you can see that velocity is positive from 0 to 2, acceleration is negative from 0 all the way to 3. But right in here, from 2 to 3, you have velocity is positive and acceleration is also positive. So that would be the interval over which the particle is speeding up. The particle is slowing down when the sign of velocity and acceleration are opposite. So in this interval right here, velocity is positive, acceleration is negative. So that would be where the particle is slowing down. And from 3 to 4, velocity is negative and acceleration is positive. So that also would be an interval over which the particle is slowing down. All right, so there's our final answers. This example says if a ball is given a push so that it has an initial velocity of 5 meters per second down a certain inclined plane, then the distance it is rolled after t seconds is given by the function 5t plus 3t squared. Find the velocity after 2 seconds. Velocity is the derivative of the position function, so we take the derivative of this function and we get 5 plus 6t. And now we plug in 2 for t, so we get a velocity of 17 meters per second. Part B says how long does it take for the velocity to reach 35 meters per second? So we take the velocity function and we set it equal to 35 and we're going to solve for t. And we end up getting 5 seconds. This example says consider a population of bacteria in a homogeneous nutrient medium. Suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. If the initial population is n naught, which equals 100 bacteria, and the time t is measured in hours, what is the rate of growth at time t equals 4 hours? I wrote a note here to refresh our memory. I wrote, since the population doubles every hour, and its initial population is going to be 100 bacteria, the population function is going to be written n of t equals the initial amount, and then because the population is doubling every hour, there's our rate of growth. It's going to be 2 raised to the t, and then I plugged in 100 for the initial amount, so we get 100 times 2 to the t. Since we want the rate of growth, we're going to take the derivative of this. To take the derivative, I'm going to drop the 100 down, and now we're taking the derivative of the function 2 to the t. When you have anything of the form a to the x where a is the constant, the derivative is going to be a to the x ln of a. We have 2 to the t, so the derivative is going to be 2 to the t ln of 2. And finally, we're going to plug in t equals 4 hours into our formula. I plugged in 4 for t, and now we're going to plug this into a calculator. And if the problem doesn't specify otherwise, we're going to round to 3 decimals. So we get 1109.035. This example says, suppose a company has estimated that the cost in dollars of producing X items is given by the cost function 10,000 plus 5x plus 0.01x squared. Part A says find the marginal cost function. So to do that, we're going to take the derivative of the cost function. The derivative of 10,000 is 0. The derivative of 5x is 5. And here to take the derivative, we take the 2 and we multiply it to 0.01, and then we subtract 1 from the exponent and we just get x. So here's our marginal cost function. Part B says find C prime of 500 and using correct units, explain the meaning of your answer in the context of this problem. When we plug in 500, we get $15 per unit. And I wrote it out. C prime of 500 represents the rate at which costs are increasing is $15 per unit with respect to the production level when x equals 500 items. Part C says compare C prime of 500 with the cost of manufacturing the 501st item. To find the cost of manufacturing the 501st item, what we do is we take the cost of producing 501 items minus the cost of producing 500 items, and that will give us the cost to produce just the 501st item. So we're going to plug 501 into the original cost function, and we're also going to do the same with 500 into the original cost function. So we're going to subtract these. So to manufacture the 501st item, it costs $15.01. And if you'll notice, that is very close to C prime of 500. And I wrote this out. C prime of 500, which was $15 per unit, is approximately equal to the cost of manufacturing the 501st item, which we got right here. This example says sodium chlorate crystals are easy to grow in the shape of cubes by allowing a solution of water and sodium chlorate to evaporate slowly. Part A says if V is the volume of such a cube with side length x, calculate dV/dx when x is equal to 3 millimeters and explain its meaning. Remember, the volume of a cube is going to be x cubed. We're going to take the derivative of this with respect to x. So we get 3x squared, and now we're going to plug in 3. And you get 27 millimeters cubed per millimeter. And I wrote it out, 27 millimeters cubed per millimeter is the rate at which the volume is increasing as x increases past 3 millimeters. Part B says, show that the rate of change of the volume of the cube with respect to its edge length is equal to half the surface area of the cube. So the rate of change of volume of the cube with respect to its edge length is going to be 3x squared. And we want to show whether or not this rate of change is equal to half of the surface area of a cube. So for your cube, you have the area of one side would be x squared, and then we have how many sides? 1, 2, 3, 4, 5, 6 sides. So that'd be 6x squared. So half of 6x squared is 3x squared, and it checks out. All right, guys, thanks for watching.